Good morning, guys. So today we are going to talk about cell potential. And so cell potential is essentially the voltage that occurs across the half cells of the electrons. And remember, we kind of looked last time and we talked about or in our last notes, we looked at a voltmeter to measure the voltage. So again, this is just the voltage measured. But really what cell potential is it's the driving force of the reaction. It's the pull of the electrons across the wire, or sometimes it could also be like the push of the electrons across the wire, but it causes our reaction to take place. And we can think through these cell potential with also about it like being spontaneous and non-spontaneous. So anything that has a positive cell potential or E cell are always going to be spontaneous. If it has, or thermodynamically favorable is our better word to use there. Whereas if it has a negative cell potential, it's going to be non-spontaneous. We use the units of volts and we measure it using a voltmeter. And at standard conditions, E cell standard is equal to E cell oxidation plus E cell reduction. And again, standard potential is the sum of the standard oxidation potential for the oxidation reaction and standard reduction potential for the reduction half reaction. And standard conditions are always going to be 1 atmosphere for gases, 25 degrees Celsius, and if you have a solution, it'll be a 1 molar solution. If it's not standard conditions, then it's still the same equation. It's just that we can't use our standard cell potential chart to figure out our cell potential. So we do have standard potentials. All right, you can see this is a chart. This is very similar to something you would find in your textbook or online. If you Google standard reduction potentials, this is what you have. All right, so these are basically kind of our numbers, I guess, for our E cell or our cell potential. So these are all going to be for different half reactions. This is basically what their standard reduction potential is. All right. So they're typically written as reduction reactions. So if you'll notice, every single one of these is gaining electrons. So it is a reduction. All of them are written as reduction reactions. Now we know in our actual chemical reactions that we have to have a reduction paired with an oxidation. Reduction can't happen if oxidation doesn't happen. So if I did want to look at what would be the cell potential of an oxidation reaction, reverse your reaction, and then reverse your sign of your potential. So like, for example, if I have this cobalt one right here, for reduction, my cell potential is 1.92. Well, if I have oxidation, then it would be negative 1.92. So I just reverse the sign because I'm reversing my reaction. Basically, we can't determine these directly, but we use a standard hydrogen electrode, which we just kind of have assigned a value of 0. So this is what the hydrogen electrode looks like. It's a platinum electrode that is coated in hydrogen, and we just say that its cell potential is 0. And so we use that, then we can measure the volts that it takes to get across, and that is how we are able to determine the reduction potential of, or the cell potential of the other ones. So all other half reactions are based on the standard hydrogen electrode. Substances with more positive reduction potentials are more easily reduced, and so they're going to act as oxidizing agents, or they're going to cause something else to be oxidized. And then the more positive the reduction potential, the stronger the oxidizing agent. So the higher, the more positive is, the more likely it is to cause something to be oxidized. So like, for example, cobalt has a really high reduction potential, and so it's going to be, most likely it's going to be reduced and cause something else to be oxidized. And then the more substances with negative potentials are going to be more easily oxidized. So again, if it has a negative potential, like aluminum down here, it's a really negative potential. It would have a really positive oxidation potential. So it's going to be more easily oxidized. So it's going to be a reducing agent, cause something else to be reduced. The more negative the reduction potential, the stronger the reducing agent, the more likely it is to cause something else to be reduced. Now, like I said, this is just kind of a show you the setup of a standard hydrogen electrode. Nothing super exciting there. One thing to note is that sometimes what we're going to be doing when we are combining these reactions is it's going to look a lot like Hess's law. Again, we're balancing reduction reactions, not really Hess's law. We're balancing reduction reactions or redox reactions. I don't know why I said reduction. We're balancing redox reactions and then calculating the cell potential. So sometimes when we're balancing redox reactions, we have to multiply our reactions by a factor. This is really important. You do not multiply the cell potential by any factor. So cell potential, it's independent of amount. Your cell potential, it doesn't matter how much you have, it's going to stay the same. So it's an extensive property. So we do not multiply the cell potential. All right. And so if our cell potential is positive, the reaction will be thermodynamically favored. If the cell potential is negative, it's not thermodynamically favored. And what's going to happen is our electrons are always going to flow in a way that will make E cell positive. So even if they don't tell you who's oxidized and who's reduced, we can figure it out because it's going to flow in a way that makes it positive, makes it spontaneous. Okay, so let's look at this first reaction right here. So what will be the spontaneous reaction? So again, we want that positive cell potential, all right, between this following set of half reactions. And then what is the value of our cell potential as well? And what is our overall reaction? All right, so right now, again, we see we have two reduction reactions because we have two places where we are gaining electrons. One of our reactions has to be oxidation and the other has to be reduction. So we have to reverse one. Again, E cell needs to be positive. So for this to happen spontaneously, so what's going to happen is my one that is like keeping me from being positive is the one that's going to be flipped. All right, so this one, well, not that either of them is keeping me from being positive, but this one's going to be flipped because my cell potential is negative, it's lower, and so it's more likely, again, to be oxidized because it has that lower cell potential there. So that one is going to be the one that is flipped. And then we both need to multiply both of these by a factor in order to get them to be equal, our electrons to be equal. So I have 3 electrons there, 2 electrons there. So I'm going to multiply this one by 2 and this one by 3. So I'm going to flip my first reaction and I would end up with 2 CRS. And that will yield 6 electrons plus 2 CR positive 3. And our cell potential is, again, not multiplied by that factor. So all that's changed is since we flipped the reaction, we flip the sign of our cell potential. So our cell potential is 0.74. And then for our second reaction, don't flip it, just multiplying it by that factor. So I have 3 MnO2 plus 4, oh, it's not 4, 12 H plus 6 electrons yields 3 Mn positive 2 plus 6 H2O. And our cell potential there would be 1.28. We didn't change it. It's not multiplied by that factor. All right, so then we combine our reactions and get rid of what's the same on both sides, which really the only thing that is the same on both sides of these reactions is that 6 electrons. So to get my overall reaction, I would just add them together, just like we do in a normal redox reaction here. It's a long one. And our cell potential is just going to be the sum of our two, our overall cell potential is just going to be the sum of our oxidation and our reduction. So E cell is going to be 1.74 plus 1.28, which gives us an E cell of 2.02 volts. And that's it. That's how we figure out the cell potential. So hopefully that wasn't too complicated for you and you kind of understand. In general, this is a big generalization. One of the things that's kind of helpful for you, and if you're trying to figure out the cell potential or whatever, is that the anode is traditionally drawn on the left and then the cathode would be on the right. Now, on the AP chemistry exam, don't count on that. It's probably not going to happen, but it could be helpful if they're asking you to identify who would be the anode and who would be the cathode when talking about these cell potentials as well. Okay, so cell potential also relates to spontaneity, like we've talked about. If it's positive, it can be spontaneous. So we can relate that back to Gibbs free energy, which ties in all of that stuff that we were talking about in our first unit. And so what you're going to see is that this unit that we are talking about now relates to our first unit as well, or the first part of this unit, as well as it also relates to equilibrium. So it relates to thermodynamics, relates to equilibrium. So you can see that this could definitely be one of those ones, a free response question that could tie in a lot of different units. So yeah, just to let you know. So let's talk about that relationship. So the more positive the cell potential, the greater the thermodynamic favorability of the reaction. So since delta G, K, and E cell are all measurements of thermodynamic favorability of a reaction, we can actually write equations to interrelate them. So this first one is for delta G, and delta G is equal to negative N F times our cell potential. So delta G is just the standard free enthalpy change. N is number of moles of electrons. F is a Faraday, and a Faraday is a constant value. All right, so don't worry too much. It's a constant value, and it is found on your periodic table. Sorry, I don't know why I was struggling so much. I couldn't think of that word. It is found on your periodic table that you'll be given, so your equation sheet. But basically, a Faraday is an amount of electricity that reduces one equivalent mass of a substance at the cathode and oxidizes one equivalent mass of a substance at the anode. Again, so it's basically the amount of electrical charge carried by 1 mole of electrons, and that is 96,500 coulombs per mole. All right. Again, this is just a constant value, so it's not something you have to figure out, and it is given to you on your chart, on your formula chart. And then E is standard potential. If E is positive, delta G is negative. So that's just one of the equations that we can use to convert between cell potential and delta G. Now remember, to find K, we know delta G is equal to negative RT times the natural log of K. So you can see that this already is relating to units, because we could use our cell potential to find our delta G to find our K value there as well. So that's all interrelated, guys. It's coming back. It's all interrelated. All right. So that's all at standard conditions. Let's talk about non-standard conditions now pretty quickly. All right, so remember, standard conditions are 1 molar at 25 degrees Celsius. And since these are 1 molar and 25 degrees Celsius, their Q value, and remember Q is our whenever we're not at equilibrium and trying to figure out how to get to equilibrium. So these are going to be Q equals 1. Now, if our cell conditions are not standard, so not 1 molar and 25 degrees Celsius, the cell potential will be affected. And we can calculate this effect by the Nernst equation. Now, I do want to go ahead and tell you that the Nernst equation is not required on the AP chemistry exam. So I am going to talk through what the Nernst equation is, but it is not actually required on the AP exam. However, we should be able to talk about whether or not changes in concentration are going to increase or decrease a cell potential by using Le Chatelier's principle and those Q values, all right, that we've talked about. So R is just that constant value in this equation. T is temperature in Kelvin. Q is the ratio of concentration of products over reactants raised to the power of their coefficients. It's just how we would normally solve for Q. N is number of moles of transferred. F is Faraday's constant. This is another way you could potentially see the Nernst equation if it was at 25 degrees Celsius. Now, again, this equation is not required on the AP chemistry exam. You could, however, use it, but I just wanted to introduce it to you, show it to you, so you could kind of see. So now let's talk about how we can know how changes in concentration are going to affect our cell potential without having to use that long, complicated equation. So under standard conditions, when Q is equal to 1, the reaction is not at equilibrium. The cell potential value is always calculated at the beginning of a reaction, but as a reaction progresses, our cell potential decreases till it reaches 0, and when we reach 0, the battery is at equilibrium, aka our battery is dead. So when you have a dead battery, all that means is that battery has finally reached equilibrium, and yes, it may be dead and useless to you, but the battery is at equilibrium now. All right, so in a voltaic cell, K is greater than 1, so we can use Q to help us figure out basically our K value is greater than 1, so it's going to be like products favored. So when Q is larger than 1, the system is moved closer to equilibrium, and the cell potential is going to decrease compared to under standard conditions. Now, when Q is smaller than 1, the cell is further from equilibrium, and the cell potential will increase compared to under standard conditions. So let's look at the following reaction. So I have aluminum reacting with manganese. So we want to predict how E cell under non-standard conditions, that's this one, compares to E cell under standard conditions. And we know it's standard conditions because it has that little circle right there. That tells us the kind of degree sign that tells us standard conditions. All right, so let's look at this first one. So first thing we want to figure out is just what would our Q expression be? So Q is just the same way we solve for K. So it's going to be products over reactants, and solids are not included. So this would be Al positive 3 raised to the second power over manganese positive 2 raised to the third power. All right, so let's look at this one. So Q is going to be equal to 1.5 squared over 1.0 to the third power. Now, I don't even need to solve this one to know that my Q is going to be greater than 1, right? So I don't even need to solve this one. So my Q is going to be larger than 1, which means that my new cell under these non-standard conditions is going to be less effective as compared to my cell under my normal cell potential. Again, it's like we have too many products here, and so we're just closer to equilibrium, and so our cell potential is going to decrease because our Q is going to be greater than 1. So it's closer to reaching that equilibrium. So our cell potential is going to be less. Our reaction is not going to run for as long. All right. So for our second one, then we have, again, our Q value. It's the same equation. So our Q value here is that we have 1 molar of aluminum over 1.5 molar manganese raised to the third power. So here, again, I have 1 over not 1. So I can see that my cell potential, without even solving it, that my cell potential is going to be less than 1. So my cell potential here would be greater than my cell potential at standard conditions because it's less than 1. So we're further from equilibrium. So our cell potential is going to increase and our reaction is going to run for longer. All right. Let's talk about this last one now. I actually want you guys to go ahead and try to look at this one and try to answer it. And then, and then we can go over it. All right, so go ahead and try and answer this one. Okay, so what we see is that we have our Q value is 20. So Q is huge, and we see that we have a lot less reactant concentration than product concentration. So our reactant concentration is 0.020 versus our product concentration, which is 0.4. So we have a lot less reactant concentration. So our Q is going to be greater than 1. So our voltage is going to be lower because we don't have that driving force of our reactant to make our reaction happen. So our reaction is just not going to happen for as long. And so our voltage would be lower, or our cell potential would be lower because, again, our Q is less than 1. And so we're already closer to equilibrium. And so our reaction is just not going to happen for as long. All right, guys, that is cell potential. Today, you should continue working on your skill builder. This should help you guys be able to complete a lot more of it. Next class, we're going to talk about electrolytic cells, Faraday's constant, and it'll be our last day of notes. All right, have a good day.